Hello, this is the next video in a playlist that I'm calling hypothesis testing, and here this is a follow-up video to a video that I called two-sided uniformly most powerful unbiased test binomial. And so we're in that same exact setting, but we're going to use the R software to solve for the critical regions. The hypothesis we're testing is that P is equal to some value called P naught versus that it's not equal to that value. And let's just jump right in. So I like to remove all the objects or make sure they're removed before I start a program. Here we're going to assume our hypothesis test is that P is equal to 0.75. We're going to use an alpha of 0.05 and a sample size of 55. Now my approach is I create all possible combinations of C1 and C2 that we could have for a binomial of size n. So that's column 1 will be from 0 to n, column 2 will be from 0 to n, but all possible combinations. Now, because it's all possible, it creates situations that we can't have. C1 being equal to or greater than C2, we can't have that. We're going to assume that C1 is always less than C2, so we get rid of them in that second command. Now, these constants here, the K1 through K6, that's in this video they're considered constants, and I don't use C1 through C6, constant, because that we're saving for critical regions, so I just call it K. But we assume that we know the C1 and C2, the points that start the critical region. And then we solve for the gamma 1 and gamma 2 part of the randomized hypothesis test that would force that rejection region to be 0.05. Now, if C1 and C2 are not the correct values, then the gamma 1 and gamma 2 needed to force that to be an alpha level test get really weird, and not between 0 and 1, which are required for a test function. So we calculate the C1 or the K1 through K6, and then what that does is it creates two equations, two unknowns. So in one equation you solve for gamma 1 and plug it in the next equation, solve for gamma 2. And that's what this highlighted portion is we're solving for the gamma 2. Then we take gamma 2 and put it back in the first equation and then solve for gamma 1. And you can kind of see that there's a gamma 2 in this second equation. And now we have them. And this finds a solution for all possible combinations. But since gamma 1 and gamma 2 have to be between 0 and 1, we get everything that doesn't fit within that region. And it turns out that this test is essentially unique. It is unique except for the weird cases, and so that's why I say essentially unique. So let's calculate the type 1 error, or the alpha level. That's what this does, and now let's check it to see what it says. So our cutoff is 35 and 47. The gamma 1 and gamma 2 are these, and in calculating the type 1 error, it is a 0.05 level. Now let's calculate the power curve for this test. Notice here in this function, P binom is sort of the cumulative distribution function, and so we pick a point, C minus 1, and n is the size of the binomial, P is the probability of success, probability of a 1. And notice it's x. Our test function is a function of that probability of P. So when we plot the curve for these lines, we plot them and it looks like this. And so this is the power curve for this hypothesis test. And notice that at 0.75 we're right here, and the dotted line is 0.05 level. And notice that every point in the alternative region is above that, and it has to be because it's an unbiased test. If it were not unbiased, it would dip below it somehow. So this is the power curve for the uniformly most powerful unbiased test in the binomial setting. Now I'm going to point something out here. 0.6, if we go up here and then over, 0.7, 0.69, 0.68 is where we are in that curve. And I say that because we're going to do a little computer simulation. So I store the constants C1, C2, gamma 1, and gamma 2 in their own variable. We're going to do 1 million replications. We're going to create a vector of binomials of size 1 million, or the vector size 1 million, the binomials of size n, and we're going to assume the true probability is 0.6. Now remember, this test was developed for the assumption that it's 0.75. Here just calculates the number of times we would reject, we table it, and when they calculate the probability of rejection. So it's 0.67. And so I'm going to go back here. So at 0.6, it's right there. Yep, so it is probably 0.67. So 0.7 would be there, 0.67. So it is very accurate, very close to the theoretical. Now what I want to do is use the equal tells approach. I want to calculate the C1, C2, gamma 1, gamma 2, etc. for the equal tells. And now the uniformly most powerful unbiased test, the probability of being in the left tail or the probability of being in the right tail is not equal, it's not the same. But in the equal tells approach it is, and so this is what it is. Now the C1 and C2 are the same. Now these gamma 1 and gamma 2 values are from the uniformly most powerful unbiased test. And these gamma 1 and gamma 2s are from the equal tell test. Now they both end up being a 0.05 level test because we're forcing them to be. But what I want to do next is create a power function for this equal tells approach. And so that's the power function right there. And now I want to slowly zoom in on these two different power curves. Remember, the power curve for the equal tell test is not unbiased. So let's look at it here. So this is from a high level standpoint. And look at the two curves. They are essentially unique. The line that you can sort of see that there's two lines, or at least I can from my screen. I don't know if you're able to from your viewpoint, but essentially the same. And they definitely both look unbiased, above the 0.05 level. And now I want to zoom in just a little bit. So we'll zoom in, say 0.1 plus or minus 0.1 to that 0.75. And now let's look at it. So we're a little bit closer, and you can see the two curves are not the same, but they're really, really close, and they still look sort of unbiased. You can't tell that either one of them dips below the 0.75 cutoff value. So let's zoom in a little more. Let's zoom in 0.01 to either side of 75. And now you can tell the two curves are definitely different, and the equal tell test dips below the alpha level, 0.05. And so it's not an unbiased test, but the power curves are so close, and it's so much easier to calculate the equal tell test that most people just do that equal tell test. Now I'm going to zoom in one more time, and then we'll call it quits for this video. Here we're zooming in really close, and you can tell that it does dip below. Now I've zoomed in so close it looks like these are huge differences, but remember, on that first view they look like identical curves. And so the fact that there's a difference here, but it's only it's difference in 10,000ths of a probability, they're essentially on top of each other. Okay, well that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.